So today we're going to continue on with chapter 6 and talk about alpha decay and other applications of quantum tunneling or reflection. So alpha decay is when an unstable nucleus eliminates excess energy by spontaneously emitting a high energy particle. And that higher energy particle is going to be an alpha particle. So this unstable nucleus emits this alpha particle and leaves behind what we call a daughter nucleus, which is at a lower energy state after the decay. I've drawn a little cartoon of an alpha particle here. It's going to be made up of 2 neutrons and 2 protons. Together, neutrons and protons, because they live in a nucleus, are called nucleons. But that's our alpha particle. So I'll give you an example here of an alpha decay. You could have uranium, and specifically uranium-238, that then becomes thorium-234 plus an alpha particle. So the 238 and 234 are just how many nucleons, protons and neutrons, are in the nucleus of these 2 things. So thorium is our daughter nucleus from that uranium alpha decay. Now the daughter nucleus and the alpha particle are both going to be positively charged, so they're going to repel each other. So protons and neutrons in our nuclei are held together by the strong force, which is one of the fundamental forces. And that strong force overcomes the electrostatic repulsion in a stable nucleus. Strongest at when those things are in contact. But when our nucleus gets very large, that strong force isn't enough to hold that very large nucleus together, and that's why we have like an alpha particle breaking off. So an alpha particle is at a point of maximum potential energy when it's at the nuclear surface. All right, so we're going to model this alpha particle breaking off as tunneling through a potential barrier created by that strong force. So we're going to go ahead and look at that. All right. So the alpha particle being at a point of maximum potential energy when it's at the nuclear surface, when it's just at the edge of being contained by this nucleus, is going to be maximized. So we're going to go ahead and look at thorium, which has 90 protons, and an alpha particle, which has 2 protons. So if that alpha particle is sitting at the surface of a thorium nucleus, it is at this distance, 7.4 times 10 to the minus 15 meters from the center of the thorium nucleus. So in that case, we're going to have an electrostatic potential energy that we can write from our just plain old physics 2 kind of equation where we've got 2 charges and we've got some radial separation distance. In this case, our 2 charges are our alpha particle, so it's got 2 protons, and our thorium nucleus. So we're just going to look at the thorium nucleus like it is 90 protons with that center of electrostatic charge being at the center of the nucleus. And we've got epsilon 0, we've got that constant somewhere in the back of the book or back of our head. And we've got this radial distance between the centers of charge. Right? So we'll plug all that in and say, yeah, the electrostatic potential energy for our alpha particle is 5.6 times 10 to the minus 12 joules. Or if we want to convert it to other units, that is 35 mega electron volts. So if that's the case, when a uranium nucleus decays, the alpha particle at the surface of the daughter nucleus, the daughter thorium nucleus, should have 35 mega electron volts of electrostatic potential energy and would speed up as it's repelled away. So if that's its potential energy, as that alpha particle gets very far away, it is going to move towards having a kinetic energy that should approach 35 mega electron volts. So far away according to conservation of energy, where our kinetic energy, our potential energy are equal to each other, right? The sum of all energy is equal to each other no matter where we are. But experimentally, put in a big old but, experimentally what we actually see is a much smaller kinetic energy. So experimentally, that alpha particle is detected with a kinetic energy of only about 4.3 mega electron volts when we're far away. So we want to look at what is going on there to make experiment disagree so much with what we would predict from this electrostatic potential energy of an alpha particle right at the surface. One explanation for this difference in expected versus actually observed kinetic energy is that the alpha particle never had 35 mega electron volts of energy to start with. So if we look at the alpha particle only ever having that 4.3 mega electron volts of energy that it has when its kinetic energy very, very far away, we can see that the alpha particle actually had to tunnel to get away from the nucleus. So you can see this in the figure 612 in your book. This is just an energy diagram where that orange line, let me highlight it for you. This little hump here, it's labeled U for our potential energy, and that's the potential energy barrier that our alpha particle needs to overcome to get away from the nucleus. Now, since we say far away, it only has this 4.3 mega electron volts of energy. That's the total energy that our alpha particle has. So we have that potential energy barrier that our alpha particle needs to tunnel through. And this is just an application where we can use that potential energy barrier equation that we derived in our last class. So here, when we're in the nucleus, the alpha particle, or the protons and neutrons that make up the alpha particle, can move freely around in this nucleus. So our potential energy is 0 here. But the surface is a barrier where the other nuclears are trying to draw that alpha particle back in via the strong force. And that alpha particle is going to tunnel out through the barrier. Outside the nucleus, the alpha particle experiences only electrostatic repulsion, and so that's where we cause the potential energy to rapidly drop as the strong nuclear attraction rapidly drops off with distance. So when we talk about radioactive decay rates or alpha particle decay rates, what we really might talk about are transmission rates of alpha particles being able to transmit through this barrier. So that's how we're going to look at these. So again, we can look at decay rates as transmission rates. So I'm going to look at the number of decays per time. In other words, if I have a sample of uranium with a bunch of uranium atoms in it, I'm going to look at how many of those atoms decay, say, every second into a thorium atom, and emit an alpha particle in the process. That's what I mean by number of decays per time. So what we're looking at is how many times would an alpha particle strike the barrier, say every second, and what's the transmission probability? What's the probability that that strike results in the alpha particle tunneling through that potential energy barrier? So we could say one strike happens every time an alpha particle manages to cross the width of the nucleus. And we have our transmission probability given by that function t that we solved before. So how fast is that alpha particle freely moving around the nucleus? And how long does it take to cross that diameter? Right, so that is a rate, that is a distance, and we'll multiply that by our transmission probability. And that'll give us the decay rate, or the number of decays per time. Now, it's kind of wild that the alpha decay, the low energy of the alpha particles, completely gets explained by quantum physics and not by classical physics. And in your textbook, there's a table that gives you energies, or typical energies of the alpha particles emitted by alpha particle decay, and the mean time for decay to happen. So that's an average time, kind of given by this equation here that you have. Other examples and applications that are worth looking at are things like the tunnel diode. So there's a short section in your book that talks about tunnel diodes. So the tunnel diode just exploits this idea of tunneling, and a tunnel diode will have a quick response to changing voltage. So it's used as a high frequency switch in electronics. You've also got things that are called squids. I love that. Squids are superconducting quantum interference devices. So sure, let's put that down. Superconducting quantum interference devices. Squids use a tunnel junction with superconductors. They use a tunnel junction, which is two conductors separated by an insulating barrier. And then a Josephson junction is a tunnel junction with superconductors through which electrons can tunnel in pairs. So that Josephson junction is actually central to the workings of a squid. The insulator acts as a weak link between the charges and the charges motion on the two sides of the junction, which couple them like a weak spring would couple a pair of pendula. So there's a diagram in your book that kind of shows that. Now, when they're coupled like that, the energy flow is dependent on the phase relationship of the two things oscillating on the two sides. So our charge carrier wave functions can be constructive or destructive interference in a squid. In the case of the squid, the phase relationship of the charges that are separated by the weak link, it's very sensitive to any nearby magnetic field. So squids can detect extremely small magnetic fields, including those produced by the human heart or the human brain, which makes them really useful devices. And then you've also got in your textbook a little information about field emission. So field emission, when we want to remove an electron from a given metal, we're going to require a minimum amount of energy. We already talked about that. We talked about that in terms of the work function. So when we talk about field emission, we can picture electrons residing in a potential well. Due to their attraction to positive ions, they get reflected at the well by a potential step. So when we bring a positive electrode, an anode, near the potential step to change it into a potential barrier, the electron's moving too slowly to mount the work function barrier might tunnel now. This is known as field emission, can be used as an alternative to thermionic emission, where you have electrons boiled off a cathode by heating. So if you've heard of a field emission transistor, this is what is used there. So quantum tunneling is used in a lot of our modern electronics. Also in this section, they talk about the scanning tunneling microscope, which I think I've mentioned in class once or twice or more. So a scanning tunneling microscope is basically where you have a tip that scans across a surface, and when the surface has some topography to it, you've got this variable barrier width between the tip and the surface where tunneling can occur across that air gap, across that barrier. So changes in tunneling current corresponds to changes in the barrier width, and you can get very small details resolved down to like atomically small details. Okay, and you can use the wide barrier approximation with your scanning tunneling microscope. So they go through that example in your textbook. So we'll wrap it up there. We'll start with particle wave propagation in next time.